And the next talk, which I think is the final talk before the break, is online. Is Syed Naqvi. Can you share your screen, please?
Yeah. Can you see the?
Yep, absolutely. Yep, we can see without any problem at all. That's great. So yeah, so Syed, sorry if I've massacred your name.
It's fine.
Is going to talk about spin-induced moments, tests for inspiraling compact binaries on eccentric orbits.
Okay. Hi. So I'll just start my timer. So hi everyone. I am Syed Naqvi. I am a postdoctoral fellow at IIT Madras in India. I'm working in the gravitational group of Chandrakant Mishra. And basically, what I will be talking is kind of a cartoon which you see in front of your screen right now. So we notice two things. That first, that there are these objects which are obviously moving around each other. But first thing we notice is that they are moving in an eccentric orbit. And the second thing, which I have kind of exaggerated here, if you see at that blue blob, you see that it is kind of wiggling, right? So there is something which is called the spin-induced moments, which is happening due to the spin of the individual object. And the main idea would be to study these spin-induced moments in eccentric orbits and try to pitch them as tests for inspiral compact objects, because different kind of compact objects will have different imprints in the gravitational wave signature, which we observe in the detector. So this is the kind of the content of my talk. So we know that eccentric gravitational waves are going to become important, because if we do not include them in our data analysis studies or in theoretical templates, then these can bias our study. Then I will try to talk about the spin-induced quadrupole moment, which I will denote by SIQM. And then, as we know, that gravitational wave templates are obviously very important, because you are using millions, or let's say more and more templates, in order to find that very fine needle in the very noisy data. So there I will only speak about the post-Newtonian waveform, where I will try to show and not scare you guys that how this SIQM, which is depends on this kappa parameter and eccentricity, comes into the picture. And finally, I will just try to show some preliminary parameter estimation studies, which is done with the help of Fisher matrix. And the main idea would be to just take a 3.5 post-Newtonian spinning circular waveform, which has these kappa terms, and do only two things. One, you add 3pn non-spinning eccentric terms. So you are only adding kappa. The other thing is you add 3pn eccentric but spinning terms. So that will have kappa, and see how the errors in kappa, do they improve or not. That's the idea. So for gravitational wave templates, we know that as the binary is evolving from inspiral to merger to ring down, we know that there are these three theories which we kind of use. One is the post-Newtonian, then during the inspiral, then during the merger, we have the numerical relativity, and finally, we have the black hole perturbation theory. I will only focus on post-Newtonian theory, and main idea would be to look into this guy, the psi, that would be kind of the protagonist of this talk, and how eccentricity and SIQM enters over here. Now, the case for first, I would like to speak about the case for eccentricity. So, we had like two very detailed talks just before my talk. So, I won't be going into much detail. But here we know that in binary evolution, there are two major scenarios where, on one side, you have isolated binary evolution, where the binaries would have shed their eccentricity and they will circularize by the time they enter the detector. But the other and more important for this talk would be that if there are binaries formed in globular clusters or by three body interactions, then they might retain eccentricity. And then if you do not include eccentricity in your gravitational wave analysis, then this can kind of lead to model uncertainties, and this would result in a lack of gravitational wave statistics. Now, the case for spin-induced quadrupole moment is very simple. So if you look at the cartoon on top, so there is a sphere which is kind of rotating. We know that if when the Earth is rotating, it is kind of bulged, right? So due to the spinning of the object, there is a deformation caused in the spinning object. So what happens is that the spinning motion of a companion, this creates a distortion in its mass distribution, and which creates a distortion in the gravitational field outside a star or any compact object, which is measured by the quadrupole moment. So this quadrupole moment, or more specifically here, spin-induced quadrupole moment, is dependent on this SIQM parameter kappa, the spin chi a, and the mass ma. And this was studied by Poisson and Kidder earlier. But more importantly, what happens is that the value of the spin-induced moment is actually is uniquely defined according to general relativity as one for black holes, and is of a different value for neutron stars, black holes, neutron stars, boson stars, or so on and so forth. So the main idea is that if you have two spinning objects which are moving around each other, emitting quadrupole radiation, but if there is deformations produced due to the spin, then the gravitational wave signature is essentially different. And the main idea of studying this SIQM, and which people have done, is to promote it as a no-hair theorem test. Because if I have, let's say, two gravitational wave objects which are moving around, and if there are black holes or if there are neutron stars, because this value of kappa will be different, so one can use then try to answer this question, that is this object truly a Kerr black hole? Or if I have neutron stars and boson stars, depending on the equation of state, the kappa is different. So this can also be used as an astrophysical identity test. And moreover, you can also use this SIQM, spin-induced quadrupole moment test, as deviations from the general relativity predictions, like if you have some non-GR theory. And this is the post-Newtonian waveform, which I hope you do not get scared of. So this is the frequency domain waveform, and we will only focus on the phase. So no amplitude corrections, only the phase. So you see that the phase is quite big, but at each post-Newtonian order, there is some effect coming. So at 1.5 pn, the beta, you have the spin-orbit coupling. Then at 2 pn, you have the spin-spin coupling, which is coming into the picture. But more importantly, alongside with this, there is the spin-induced quadrupole moment, which I showed behind. So this sigma QM depends on that kappa. And this kappa, the spin-induced parameter, this appears at 2 pn, 3 pn, and 3.5 pn post-Newtonian order. So that order depends on the coefficients of V over here. And the spin-induced quadrupole moment, this has been studied for quasi-circular binaries. And when people were when other people were trying to study it, they were trying to probe these questions that, let's say, if I have a very massive neutron stars, and if I want to compare it with a very lightest black hole, and if I have a merger of such a signal, how will I kind of get an estimate on what am I detecting? Then this SIQM can also be used to differentiate between existence of black hole mimickers, because you see that for boson stars, the kappa parameter is between 10 to 100. Then similarly for grava stars, so on and so forth. Then the earlier studies, which do the baseline which I would follow, is from Krishnendu et al. 2017 and 2019, where they first did some semi-analytical Fisher matrix analysis, where they considered a waveform which was 2 pn corrections in amplitude and 4 pn in phase. Then obviously the main or a more deeper study was done by Divijoti et al. When they did proper Bayesian parameter estimation, and they included spin precision and higher order terms. And our job is to kind of study this spin-induced quadrupole moment, but for eccentric binaries. And now I will try to show you the same post-Newtonian waveform which was developed in our group. So this is an in-spiral only waveform. So Omkar et al., who are in our group over here at IIT Madras, what they have done is they have the spinning circular part, which has been developed till 4 pm. And what they did was they took the Moore et al., which developed eccentric phasing till 3 pm, and they added the aligned spin effects to small eccentricity. So you have circular waveform on the left, and then on this black and yellow, you see that there are these eccentric terms added. But more importantly, one has to be careful that this kappa parameter, the spin-induced quadrupole moment, enters into the circular part of your waveform and in the eccentricity as well. This is what was developed in the group way. And the main idea of this work is to look at these kappa or SIQM kind of errors for the third generation detectors, which have like kind of more sensitivity. So Einstein telescope and Cosmic Explorer, and compare them with the advanced LIGO case. And the main idea or the plots which I will show will deal with this kappa S. So this is a symmetric combination, which for black holes is 1, and for and like the symmetric parameter is 1 and the anti-symmetric parameter is 0. And this is which I will try to show. So like for a very basic parameter estimation study, what we have done is we are trying to do the Fisher matrix analysis. And here this is mainly dependent on your 3 ingredients. One is the noise weighted inner product, where you have information about the template you are using and also of the detector. This SNF is the PSD of the detector. Then what you are trying to do is, when you get the inverse of the Fisher matrix, you are trying to get errors on each parameter, which is given by the square root of the diagonal entries of the covariance matrix. And more importantly, what you are trying to explore is the parameter space. So you will have this TC, phi C, M chirp, so on and so forth. So till now, the studies have been done till circular case, where you have 1, 2, 3, 4, 5, 6, 7 parameters. And now we are trying to include eccentricity. So this is the baseline configuration plots, which I will be showing in the upcoming slide. So what I have done in the upcoming plots is that I have considered 3.5 pn spinning circular terms. So there is kappa over there. I will only show plots for 1.2 mass ratio. The distance is fixed at 400 megaparsecs. And this study is preliminary right now. So it only has analytical, the Einstein telescope PhD. And what we do, we simply add eccentric terms. So the Moore et al., which has only eccentric information. This is the one set of plots. The second set of plots, which would be the main results, is now you take the Omkar et al. Waveform, which has eccentricity plus kappa updated terms over there. So this would be the idea, to look at the errors on the spin-induced quadrupole moment kappa s, this is the symmetric part, with respect to increasing total mass. So first case in this plot you see is that you have 3.5 pn spinning circular term, the usual case, and then you add only the eccentric terms over here. And these eccentric terms are only in E0 square. So on the left, you see for low eccentricity. By low, I mean I'm only going from 0.01 to 0.05. So on the y-axis, you have the delta kappa s errors, and on the x-axis, you have the increasing total mass. So you see that on the blue dashed line, what you see is that the eccentricity is very, very less over there. So these are almost circular orbits and almost circular waveform here. And when you increase the eccentricity 0.02 and you are going only till 0.05, you see that the errors are quite bad. This point goes way off because some numerical effect, but it can come out. But here what is happening is that for lower eccentricity, I see that my errors are actually poorer. But on the right hand side, if you focus on the high eccentric case, where I'm going from 0.05 to eccentricity 0.1, I mean, it's not that high eccentricity, but this is what the waveform allows us to do, the value of the eccentricity. So you see that as the total mass increases, my errors are kind of improving as when we are going towards the higher total mass. And if we see these plots together, this is what I'm trying to show over here, is that when the eccentric information in your waveform is greater than 0.05, you see that your errors are kind of better than what you are getting from the spinning circular when you only consider the spinning circular. And this kind of agrees intuitively because the systems which are higher total mass, they merge at lower frequency, so they will retain eccentricity over there. So in a way, they are kind of helping with your kappa errors, but future analysis has to be done. But now moving on to the main part, because here, just to recall that you have 3.5 spinning circular terms, and here I'm only adding eccentricity waveform, which is of Moore et al. But the main idea is to, and also here is the 4pn plot, which we see that the errors are kind of are kind of more good. So you see that for lower eccentricity, the errors are here, and when you increase eccentricity, they keep on decreasing. So here you have considered, I mean, we have considered 4pn spinning circular and adding only 3pn eccentric Moore et al. Terms. But more importantly are these plots over here, where you start with the baseline configuration of 3.5 pn spinning circular terms, kappa enters here, but more importantly, you have the 3pn eccentric kappa terms. So now your information of kappa is kind of, you have more information. Now I will just quickly go to, so on the left you have the lower eccentric case, and on the right you have the higher eccentric case. You are kind of seeing the same trend. So on the left, you see that the black line, which is for eccentricity 0.05, low for this case, you see that the errors are kind of poorer, but after a certain total mass, they start to flip. And you see better errors on the higher eccentric case from going from eccentricity 0.05 to 0.09. But
2 minutes
more important,
left.
2 minutes left. Okay. So then when you consider 4pn spinning circular terms, and then you consider 3pn Omkar et al. Terms, you see that the when you include the information about eccentricity, the errors are decreasing. But more importantly is this plot over here. So for very low eccentricity, they are giving results as the circular one. But as you increase the eccentricity, Omkar et al. Terms, which has eccentric kappa terms, is giving better errors, which kind of makes sense because you have more information about kappa over there. So to conclude, what we have done is we have performed a preliminary Fisher matrix analysis for spin-induced quadrupole moment and eccentricity, only including phasing corrections. And obviously the idea would be to include amplitude corrections, but that won't change much. Right now, what I have showed you are the results for only mass ratio 1.2. You have to also go to 3, 5, so on and so forth. And what I tried to show was that if you add only eccentric terms till E0 square, and you add eccentricity kappa terms to E0 square, how the errors look like. And we see that they are actually decreasing. And here, the one thing one has to keep in mind that you need to be careful with the treatment of the parameter degeneracies, and one has to understand correlation better. And then the future work is to understand if I include E04 corrections, which are available in the literature, how will those look? And more importantly, to do is because Fisher matrix analysis depends on you have high SNR and your noise is Gaussian in the data, but that is not what it is. So we need to do full Bayesian analysis for this. And on the left, I have just kept this preliminary cartoon over here because there are these three effects which makes Fisher matrix interesting. Because see, you went from 7 cross 7 dimensional Fisher matrix to an 8 cross 8 dimensional Fisher matrix. So there is this role of higher dimensionality. It can introduce or reduce your degenerate. The other thing is that there is eccentric kappa cross term, which are giving you more information, but you have to be more sure of whether what you are seeing is actually true by understanding the correlations better. And then also that there is this higher masses. So at higher masses, they merge at lower frequency, which are retaining the eccentricity. So that's why the errors are improving. But we all have to keep in mind that because there are order of million templates, so you have to find the correct needle or the correct template. So this is one step in finding that correct needle, first of all, and then doing Fisher matrix and in future Bayesian analysis and see whether this needle is useful or not for spin-induced quadrupole moment and in the sense of eccentric orbit. So I will stop.
Do we have any questions? I think obvious. I've actually got a couple of questions. If you could go back to those plots where you were showing the different eccentricity, just go back one more, I think. No, even one more than that. Sorry, there wasn't any numbers on the slides. I didn't notice the number.
Sorry.
Yeah. So you've got on the plot on the left, you've got 0.05 as the highest eccentricity, and then on the right, you got the 0.05, but then you go down, you go up to higher eccentricities. Why does the shape of the plot change so much between 0.05 and like 0.06?
So this is what like we have to study more. So the idea would be to now study this correlation matrix and understand the correlation between the spin-induced error kappa and eccentricity. Because I mean, this flip is more clear actually over. I mean, we can take here also. So
Yeah.
I mean, we have to kind of understand why this correlation is causing that, why this flip is happening. So maybe
Yep.
there is some new physics over here, or I still need to figure this out more by looking at the correlation coefficient between kappa, this guy, and eccentricity, and see with increasing eccentricity whether the correlation is increasing, decreasing, and why it is only happening for 3.5 spinning case, which does not happen for 4 PN spinning.
At the moment, I'm not seeing other questions. I've got a second question actually, because you were talking about you could be able to distinguish between the black holes and the boson stars. I was wondering if you could elaborate a little bit more on that. Are you able to do that today, or would we need something extra?
So we would need I mean the main right now what the analysis I showed is a very preliminary because Fisher matrix analysis is not that robust. Once I code this updated waveform in something which is called the Lal suit, which LIGO Virgo people use, then when I run parameter estimation studies with that particular updated waveform for let's say real events and so on and so forth, and then if I look into the kappa posteriors, then only I can constrain. So what will happen is that let's say if I have 5 gravitational events and if my delta kappa is only peaking at 1, then I know that these are black holes. But if it is peaking at a value which is different than 1, let's say for boson stars, actually the value goes between 10 and 100. So it will be way off than the value of 1. That might be a signature. I mean, I think that might be.
Okay. Well, thank you very much. And yeah, thank Syed again, please.
Thank you.